All right, let's go ahead and get moving. So last time we finished our discussion on uniform flow. We specifically talked about how to compute discharge for an irregular channel. So a channel composed of maybe a floodplain section along with a main channel section, as you'll often find in natural river systems. So we talked about how we could compute the discharge for irregular channels like that. And then we started our discussion on channel transition. So uniform flow applies when we have a constant bottom slope, and when we don't have any changes in the channel geometry. For any other case, we will need a different tool to analyze our system. So we started talking about channel transitions, and I gave you an example. We looked at this mystery problem where we have flow in a horizontal channel that is moving over a smooth bump on the bottom. So we have some flow coming in at the upstream end of the channel with a known velocity and depth. It encounters a rise in the bottom elevation of the channel of delta Z naught. So that is the height of the bump. And my question to you was, what happens to the water surface elevation when it encounters this bump? And we took a vote. Most of you thought that the water surface will go up. So to analyze this problem, we applied the energy equation. So if we take our flow in our open channel, we don't know whether it's going to go up, whether it's going to go down, or whether it's going to stay the same. We applied the energy equation. So we have H1 plus U1 squared over 2G plus Z1 is equal to H2 plus Z2 plus U2 squared over 2G. We're assuming that this is a smooth transition so that there's not going to be any energy losses associated with this bump. And rearranging this expression for the energy equation, we ended up with something that looked like the following. We have H1 plus U1 squared over 2G is equal to H2 plus Q squared over 2G B squared H2 squared plus delta Z. And now we have an expression in which the only unknown is H2, the depth of the water at the bump. So we rearranged this equation as a cubic polynomial. And finding the roots of that polynomial, we actually found that for our example problem, the water surface went down, which is perhaps unintuitive. So the water surface went down, and there were two possible answers from our cubic polynomial. So we got one negative root, one smaller positive root, and one larger positive root. So the possible depths, the physical values, are an H2 of about 2.496 and an H2 of 1.659. So what did these two answers correspond to? What condition did these two answers correspond to? Supercritical and subcritical flow. So this larger value, does this correspond to the subcritical or supercritical solution? Subcritical, very good. So we had a subcritical solution, and we had a supercritical solution. So can you remind me, what are some characteristics of supercritical versus subcritical flow? So if you were to describe supercritical flow, just in plain English, how would you describe it? How is it distinct from subcritical? Yes. So that would be a transition from subcritical to supercritical. When we're talking about supercritical, what condition characterizes supercritical as opposed to subcritical? Yes.
Like it occurs after a hydraulic jump.
So subcritical will occur after a hydraulic jump. But just what in adjectives, what characterizes supercritical flow? Yeah.
Doesn't it do with water surface moving slower than like the underlying water?
So we'll get to that later today. Just in terms of kind of adjectives, what describes supercritical flow? Tommy, you had your hand up for a while.
Shallow.
Shallow, so it's going to be relatively shallow. And what about the speed? Shallow and fast. So just in terms of adjectives, if we're just going to describe them, intuitively, supercritical flow is generally going to be shallower, faster. Subcritical is going to be deeper and slower. So we'll get into more formal ways to characterize subcritical and supercritical flow later on in the class, but these are kind of adjectives you can use to think about these two flow regimes. We also discussed a concept called specific energy. We're going to come back to this again today. So specific energy was equal to the energy that can be traded between the velocity component and the potential component. So it's equal to the potential energy head. So that would be the hydrostatic head plus the velocity head u squared over 2g. So we're going to talk a little bit more about specific energy and how we can use it to solve problems like this one. So we also introduced a way that we could quantify whether flow is critical or supercritical using the specific energy. So we took the specific energy, we found the point at which that specific energy was minimum, and from that we came up with a test for determining whether flow is subcritical or supercritical. What quantity did we come up with at the end of class to test whether flow is subcritical or supercritical? Yes. The Froude number, remember? So we used the specific energy. We found that at its minimum point, we had an expression that related the velocity and the hydraulic geometry. And from that, we came up with the Froude number. So this gives us a test for whether the flow is subcritical or supercritical. So if the Froude number is greater than 1, the flow is which category? Supercritical, very good. If it's less than 1, the flow is subcritical. And if it's equal to 1, the flow is critical. So remember, when the flow is critical, it's at its minimum specific energy. And that corresponds to this expression being equal to 1 from our derivation of the Froude number. If you have trouble remembering which is which, so you may forget whether greater than 1 is supercritical or less than 1 is subcritical and so on, what I'd recommend is looking at the terms in the Froude number. So in the Froude number, you have the velocity in the numerator and the area, which is tied to the depth in the denominator. So if it's supercritical, more of that energy is going to be in the velocity component. So a larger numerator means more positive. So if you're just trying to remember which is which, just remember that higher velocity corresponds to supercritical, higher depth corresponds to subcritical. All right. So we didn't quite finish our mystery problem. We found that the flow, the depth at the bump is going to go down, but we don't yet know which of these two solutions is the correct one. So how can we figure out which of these two solutions is the right one? Is it going to be the subcritical or supercritical solution? Subcritical. Why is it going to be the subcritical solution? Do we know yet? Any ideas for how we can figure this out? So we can use the Froude number to characterize whether the flow is subcritical or supercritical. The problem is that we don't know these variables at the bump itself. So we know at the upstream end whether it's going to be subcritical or supercritical. We don't yet know which of these conditions applies. Yes?
Must it always transition from one to the other?
That is a good point. So we're going to use that fact to figure out which of these solutions is the correct one. So, but you're on the right track. So we're going to need to know what the Froude number is going into the bump in order to figure out which of these two solutions is the correct one. So let's go ahead and take a closer look at the specific energy. I'm going to look at it as it goes through this transition, and we're going to try to reason about what's going to happen. So I'm going to draw my specific energy diagram again. On the y-axis, we have the depth. On the x-axis, we have the specific energy, which is equal to the depth plus velocity squared over 2g. And if the discharge is fixed and the channel geometry is fixed, this is just a function of the depth. All the other quantities will be constant. So this will be h plus q squared over 2g b squared h squared. And then we get that the specific energy is a cubic polynomial in H. So let's go ahead and draw our specific energy curve. I'm going to draw a diagonal line here corresponding to specific energy being equal to H. And then let's draw our specific energy curve. It's going to look something like this. Okay, it attains its minimum point, which corresponds to critical depth. Very good. Okay. So remember, we have here our critical depth. Everything above that point is subcritical. Everything below that point is supercritical. Everything below here is supercritical. Everything above is subcritical. Okay, so the first question I have for you is this. Is the specific energy at the bump the same as the specific energy upstream of the bump? Who thinks yes? Who thinks no? Okay, let's try this again. Who thinks yes? Who thinks no? Okay, I got a couple up there for no. So, okay, let's write out our energy equation. So we have H1 plus U1 squared over 2G is equal to H2 plus U2 squared over 2G plus delta Z naught. What is this term here? Upstream what energy? Upstream specific energy. Very good. What is this term here? Specific energy at the bump. So we have the E1 is equal to E2 plus delta Z naught. So is the specific energy at the bump greater than or less than the specific energy upstream? Less than. E2 is less than E1. And specifically, E2 is equal to E1 minus the height of the bump. So specific energy is not conserved. Energy is conserved. Specific energy is not necessarily conserved. Okay, let's go ahead and draw that out on our diagram. We have, let's say we draw a line here, and this corresponds to specific energy 1. And we established that specific energy 2 is less than specific energy 1, so it's going to be somewhere over here. I'll just draw it right here. All right, and what is the distance between these two lines here? Delta Z naught, very good. So the distance between these two specific energies is exactly the height of the bump. Okay. So how could we figure out, based on this diagram here, whether our solution at the bump is going to be subcritical or supercritical? Yes. Very good. So basically the answer is it depends, the solution depends on where we start. So there's a path dependence to the solution. So one option is we could start subcritical, and then as we transition through the bump, we move down this curve and end up here. This solution being subcritical or supercritical? Subcritical. So if we start subcritical, we'll end up at the subcritical solution.
The top part, supercritical.
I'm sorry, you're correct. Oh, no, sorry. No, this is subcritical here. I wrote this down wrong. Man, no one stopped me there. This is subcritical. Remember that supercritical corresponds to higher velocity. Sorry, this here is subcritical. This here is supercritical. So we can reason about that because, again, remember the distance between this diagonal line and the specific energy curve will be the velocity component. So note here on this upper side of the curve, the velocity component is smaller relative to on the lower side of the curve. So up here is subcritical, down here is supercritical. So if we start subcritical, we move down this curve and end up here at the subcritical solution at the bump. If we start supercritical, we move along this curve and end up at the supercritical solution at the bump. So looking at this diagram here, why was my original question to you a trick question? I asked you for flow in an open channel that encounters a transition in the bottom elevation, is the water surface going to go up or down? Why was that a trick question? It could be either one. It depends on what? It depends on what? It depends on where you start. So it depends on whether the flow entering that transition is subcritical or supercritical. If the flow entering the transition is subcritical, the water surface will go So if we start subcritical, the water surface will go down. If we start supercritical, the water surface will go up. Yes. If the water entering is at a critical point. So typically, critical flow isn't stable. It's not really maintained over any distance in the channel. It's typically only encountered as a transition point.
Alright, but then the next question is, then what if it's like near to the critical point? Like,
That's a great question. So let me put a pin in that for a second. So just going back to our solution here, which of the two solutions is the correct one? Oh, actually, we don't know yet, do we? Okay, so I'll get back to that question about entering the critical depth shortly, but let's go ahead and just finish this problem here. So how can we determine which of these two solutions is the correct one? Find the Froude number at the upstream point. So let's go ahead and do that. We have, for this problem, the Froude number is equal to the velocity times the square root of the top width divided by the square root of acceleration due to gravity times the cross-sectional area. We know that the velocity is 3 meters per second. The top width is 3 meters. This is a rectangular channel. The acceleration due to gravity is 9.81, and the cross-sectional area is 3, the bottom width, times 3, the depth. If we evaluate this, we get, at the upstream end, 0.55. So let me just write, this is at the upstream end. So is our flow subcritical or supercritical at the upstream end? Subcritical, very good. So this is subcritical because Froude number is less than 1. So we have for this problem that the flow entering is subcritical. If we go to the specific energy diagram, that means we are up here. So the water surface will go down and we will end up at the subcritical solution. So the correct answer to this problem is 2.496. So the water surface elevation will decrease from 3 feet to 2.496 plus the bottom height of the ridge, which is 0.3. So the actual water surface elevation will decrease to about 2.8. It went from subcritical to subcritical. So you may be wondering, is it possible for the flow to transition from subcritical at the upstream end to this solution here, the supercritical one? So remember, in our case, the flow transition from this point here down to this point here. Is it possible for the flow to transition from this point, go all the way around this curve here, and then end up at the supercritical solution? Let's just say for this problem, is it possible for the flow to end up at this supercritical solution at the bomb? Who thinks yes? Who thinks no? Okay, why is it not possible for this problem?
Looking to the left, only hit the critical depth, right?
So that's a good point. So in order to get to this point here, we would have to do what? The flow would have to do what? It would have to transition through the critical depth, right? So in order to end up here, the flow would have to transition through the critical depth, which means that it would have to move from this point here all the way here. What would it take to get to this point? A bigger bump, right? So it has to transition through some change in elevation delta Z max to reach that critical depth. And then from that point, it can continue transitioning to the supercritical solution. Why is that not possible for this problem? Let's go back to our picture. In order for it to arrive at the supercritical point, it has to transition through the critical depth, which means there would need to be a bigger bump before you get to this height, delta Z naught. But from this problem, delta Z naught occurs at the crest or the peak of the bump. Therefore, it can't transition through the critical depth before it gets to this point. It would need to be a different problem in which there is a larger bump before you get to this height, delta Z naught. Sorry?
Delta Z, or would bigger delta Z allow you to switch?
So if this was delta Z, are you asking what would happen if this was delta Z max here? What would happen is that you would achieve the critical depth at the crest of the bump. Typically, what will happen after that is that the flow will continue to transition to supercritical at the downstream end. And what you'll end up with is that you'll have supercritical flow at the alternative depth to H1. So what would happen is you would go all the way from E1 here down to this E1 at the opposite side. At the crest itself, it would be here.
Get some confused how we were able to figure out the height when that graph that we made isn't like quantitative. It's just like there's no numbers on that graph. We just looked at E1 and E2, and then we said delta Z. Like, how do we know delta Z naught isn't delta Z max?
Well, we can compute delta Z max. It would occur when the flow reaches the critical depth at the height of the transition. So that's actually what I'm going to ask you to do next. I want you to find the height of the bump needed to make the flow transition from subcritical to supercritical, with critical depth being achieved at the crest of the bump. So to answer your question, though, it doesn't need to be quantitative as long as kind of the structural features of this graph are obtained. So basically, all we need to know is that this delta Z naught doesn't reach delta Z max.
So, looking at the graph, right?
Well, we do, because at this point here, there will actually only be one solution. And we know that there's two solutions. So let's go ahead and take a look at that problem. What I want you to do is consider the exact same flow conditions, the exact same channel setup. So consider the same flow conditions. as the previous problem. And this time, I want you to design the height of the bump. I want you to design the bump to create critical flow. At the crest. So in other words, I want you to find delta Z max. So we have the same exact problem as before. We have flow coming in. A height H1 equal to 3 meters. U1 equal to 3 meters per second. It encounters a bump. This time we don't know how high it is. You're going to need to find the height delta Z max such that you achieve critical depth at the crest of the bump. So this here, this is your critical depth. And for reference, I'm gonna B1 is equal to 3 meters as well. I'll say as a hint, you're going to want to find the critical depth first. All right, so I'm going to give you the next 15 to 20 minutes to work on this in small groups. I have a Canvas problem posted. So this is under quizzes in-class critical flow problem. Has all of the information for the problem. So you'll need to find the critical depth, the required height of the bump to achieve critical flow, and then also the flow at the depth at the downstream end. So this is due next week. I'll give you a bit of time in class next week as well, but I want you to complete as much of it as you can today. And you'll have about 15 to 20 minutes, and I'll be walking around to help as needed. So go ahead and get started on that. I'll check in with you soon. All right, folks. So we're going to continue with this problem on Tuesday. I'll give you a bit of time in class to work. It sounds like many of you have completed the first two. Has anyone completed the third problem yet? Okay, a few of you have completed the third problem. So just to kind of give you a hint for the third problem, basically what's happening is you're starting at some specific energy E1, you're transitioning through the critical depth, and then you're ending up somewhere here on the downstream end. So there are no energy losses through this transition. Where will you end up in terms of the specific energy diagram if you go through the critical depth and end up on the other side? In other words, how does E1, the specific energy at point 1, relate to E3, the specific energy downstream of the bump? There are no energy losses in the bump. So the bottom elevation is the same upstream and downstream. And there's no energy losses. So E1 and E3 are the same. So that's how you can determine the depth downstream of the bump. So I'll give you a little bit of time on class, in class on Tuesday to work on this and finish it up. But the last thing I want to talk about is I want to give you kind of a more intuitive understanding of what subcritical, supercritical, and critical flow mean. So do you think, so we know that supercritical flow is fast and shallow, subcritical flow is deep and slow. Do you think it's possible to determine whether flow is supercritical or subcritical just by looking at it? Who thinks yes? Who thinks definitively yes? Who thinks definitively no? No hands. So let's be brave. Who thinks that it is not possible to tell if flow is supercritical versus subcritical just by looking at it? Who thinks that it is possible? Definitively. Okay, so I got some votes for yes. Why do you think it's possible to definitively determine if flow is supercritical or subcritical just by looking at it? Let's say you're in a park and you're standing by a creek and you're just looking at the water going by. Can you determine whether it's supercritical or subcritical just by looking at it? Why is it possible? If you said yes.
Gave us some adjectives to describe it, so I would use those adjectives.
I want to know whether you can definitively determine whether the flow is super or subcritical just by inspecting it. So it turns out that you can actually. And there was a comment earlier in class about how the speed of the surface of the water relates to the overall velocity of the water. I'll give you a more definitive way of characterizing supercritical versus subcritical flow in that way. So here's how I kind of want you to intuitively think about what supercritical versus subcritical flow means. We're going to talk about critical flow first, kind of as the defining case. So for critical flow, the velocity of water is exactly the same as the velocity of a small gravity wave traveling through that same water body. So let me explain what this means. Let's say we have a channel that is full of quiescent water, i.e. water that is not moving. So there is just a still body of water in this channel. The water is not flowing. Bless you. Let's say we have a still body of water. Actually, I'm gonna give myself some space on this side here. And let's say we come along to the side of this channel and we throw a pebble in. So the pebble will go into the water and it'll create a splash. And when we throw the pebble in the water, we'll get ripples or waves that form as a result of that disturbance. So looking at the side here, we have a wave front traveling to the right, and we have a wave front traveling to the left. I'm going to draw a overhead view as well. So this is our profile view. Let's draw an overhead view as well. So we have our channel. When we throw in the pebble, we'll get a series of ripples that move in all directions. If we're just considering one dimension, they'll move in the upstream and downstream direction, respectively. So it turns out that the speed of these waves is given by the following expression, c. So this is the wave speed, or I'll call it celerity. This is the speed of the wave traveling through the quiescent water. This is equal to the square root of g times a divided by t, where a is the cross-sectional area, t is the top width, and g is the acceleration due to gravity. Similarly, the wave traveling in the other direction is equal to negative g times a over t. So in the typed notes, I have a proof of this fact and a derivation for how we get this wave speed, but you can take this to be a fact that the speed of the wave moving in this water, in this still water, is going to be square root of g times a over t. So let's take a look at the Froude number. The Froude number is equal to u, the velocity of the water, times the square root of t divided by the square root of GA. And if we take this t in the numerator and move it to the denominator, we get u, the velocity, divided by square root of g times a over t. So what happens to the Froude number? Well, let's say if the Froude number is equal to 1, what does that imply about the bulk velocity of water versus the speed of a disturbance moving in that water? They're the same. So for critical flow, the velocity of water is defined to be exactly the same as the speed of a wave moving through that water. So let's think about the different cases and what that looks like for subcritical and supercritical flow. So let's take a look at a couple different cases. We're going to look at the case of still water. We're going to look at critical flow. We're going to look at subcritical flow. And we're going to look at supercritical flow. So as I showed before, for still water, let's just look at the ripple pattern that emerges over time. So if we throw a pebble into the water, we'll get something that looks like this. You'll have a ripple starting out, and it will spread evenly in all directions. Let me make this more clear. So the ripple, the wave is spreading evenly in all directions. So these correspond to different points in time. So this blue here, this is t equal to 0. Green is t equal to 1. Yellow is t equal to 2. And red is t equal to 3. So if you throw a pebble into still water, you'll get ripples that move out evenly in all directions. Let's say we throw a pebble into water that is moving with some velocity u, and that water is traveling at critical flow conditions. So let's think about what the pattern of waves will look like So we throw in a pebble at time t equals 0, we'll get a ripple like this. For critical flow conditions, the velocity of the water is exactly the same as the speed of the wave. So what does that mean about what will the wave pattern look like? Yes,
You have the two magnets together and you're drawing the.
that's a good analogy. Yeah. So basically the back end of the wave will remain fixed in place because the wave can't travel upstream. The entire wave is essentially going to be fixed in place at the upstream end. So you'll end up with something, as you said, that kind of looks like that magnetic field pattern. You'll end up with something that looks like this. Because the wave speed is exactly the same as the bulk velocity of the water. So the disturbance cannot travel upstream. This is t equal to 0. Green is t equal to 1. Yellow is t equal to 2. Red is t equal to 3. All right, let's consider the case of subcritical flow. Okay, we throw in a pebble. The water is moving to the right with some low velocity u. The bulk velocity of water is less than the wave speed. So can the wave travel upstream or not? Yes. So for subcritical flow, a disturbance can travel upstream. So we'll end up with something that kind of looks like the still water case, except biased towards the right. So we'll end up with something that looks kind of like this. It'll still move upstream, although it will be biased in one direction. And again, this is t equal to 0. Green is t equal to 1. Yellow is t equal to 2. Red is t equal to 3. Then finally, we have the case of supercritical flow where the velocity is larger than the wave speed. In this case, the entire wave will be swept downstream. So you'll have something that looks like this. You'll throw in your pebble, you'll get some ripple at t equal to 0. And then as you progress forward in time, that entire wave front is going to be swept downstream. You'll end up with something like this. Again, this is t equal to 0. T equal to 1. T equal to 2. And t equal to 3. So this is how I want you to intuitively think about supercritical versus subcritical flow. This is one way to visualize it, and one way you can kind of definitively know whether flow is subcritical or supercritical. It has to do with the relation between the speed of a disturbance moving in the water and the speed of the water itself. This is going to be important for hydraulic design because depending on your flow regime, if you make a change downstream, if the flow is supercritical, that change will not propagate upstream. Any disturbance you make downstream will not propagate upstream. If it is subcritical, that change can propagate upstream. And we'll talk a little bit about that when we get to gradually varied flow later on. So with that, have a nice weekend. And I'm holding office hours at 11:30 today. Talk about homework. See you then.